So again, welcome to our Turing-Roche Knowledge Share series. The aim of these monthly events are to bring together members of the Turing and Roche networks, as well as the wider scientific community, to hear partnership updates, different perspectives on topics in data science, and build new connections. Just before I hand over to our speakers, I'm just going to share a couple of slides on the partnership. So hopefully you can all see that. So some background to the partnership. The clue is in the name. It's a partnership between the Alan Turing Institute and Roche. Hopefully most of you will be familiar with at least one of these. But just in case not, the Turing Institute is the UK's National Institute for Data Science and AI. We're a network of university, industry, charity and government partners, and the partnership sits under our Health and Medical Sciences programme. Roche is a leading healthcare company, which is global. They have a long-term interest in personalised healthcare, and we are one of a growing number of their academic partnerships. And together we launched our strategic 5-year partnership together in June 2021. And this is our partnership North Star, so our kind of guiding aim across our 5 years of collaborating. So ultimately, we're exploring this term patient and disease heterogeneity, and we're doing this for advanced analytics. So kind of put more simply, why patients respond differently to treatment and why diseases can manifest in different ways in different people. Obviously, this is quite broad, so we're tackling this through a kind of stepwise iterative manner, which you can see illustrated on the right. With a main focus on developing methodology. And we're about halfway through the partnership, and we have focused our research into 3 different themes, staggered across the 5 years. So our first theme is structured missingness. We've funded 2 18-month projects in this area. Last month, we heard from Anthony Baptista, who was representing the network project, and you can catch up on the recording of this on our YouTube channel. And our speakers today are from the other structured missingness funded project on Bayesian modeling. Our other themes are predictive modeling, where we funded 1 18-month project and hired 2 postdocs to work on projects in this area, one on geometry of deep learning and one on conformal prediction. And our final theme is multimodal analysis. So this theme has just kicked off, and our newly hired postdoc is investigating the Cancer Genome Atlas dataset for a potential project alongside Turing data wranglers. Our core partnership team is pictured here with representatives from Turing and Roche, and then this is expanded out with researchers we've funded, Turing enrichment students we've taken on, and our cohort of community scholars. Again, you can find out more about who is kind of involved in our partnership network on our webpage. And also a key part of the partnership is wider connections and collaborations we want to build. So it's critical for us to be running events like this to get you all involved. And I know some of you may have attended this kind of event series before, and our usual format is having a Turing speaker and a Roche speaker speaking on a different data science topic. We will be continuing this format for some of our events, but we're also really excited that as the partnership research is progressing, we'll be shining a light on that at some of our events as well. So in that vein, as I mentioned, today's session will give an update from our structured missingness theme. So I'm delighted to welcome our speakers today, Mitra and Elrozy Andrinopoulou. As mentioned, we'll be hearing from them both, and then we should have plenty of time for questions at the end. Feel free to pop these in the Q&A box as we go. So I'll just stop sharing there.
No, this is great. Thank you very much, Vicky. Just to say, I'm the structured missingness theme lead for the partnership and also an associate professor of statistics at UCL. I'll just share my screen. Hopefully the technology will work. So, okay. I guess is the screen, let me just put it to full
You just
screen.
need to make it full screen, I think.
Yeah, let's hope that works. Yeah, is that okay?
Perfect. That looks
cool.
great.
All right, perfect. I think I see other stuff, but hopefully others don't see like this stuff. Okay, all right. Yeah, so as I say, I'm a structured missingness theme lead, and it's really interesting to be able to share some thoughts with you all. I should say that we're sort of in a transition point in our work. So we started with some of the fundamentals of structured missingness, really trying to understand it from a foundational perspective. But the intention is always to sort of see about how this is sort of fits in with a wider scheme of work with a partnership. goals, as in particular their partnership North Star, and a key way that it does is in the area of data integration. So I'll be talking a little bit about structured missingness and then sort of relating it to some practical challenges within data integration before handing it over to Elrozy, who will talk about a particular contextual setting where structured missingness is relevant as is data integration. Oh, let me see if I can. Yeah. Okay. All right. So, just to set the scene briefly, I mean, I imagine most people are already appreciating this, but you never know. So, good quality data we all appreciate now more than ever is essential as we want to tackle important research questions. And our setting is medical. It doesn't have to be, but it's often a a useful setting to base because everyone appreciates the importance of that. And so we maybe sort of have a set of rich clinical data, and you want to build an outcome, build a predictive model, sorry, for an outcome of interest. It could be a disease status or some other clinically relevant outcome. And so we want to build a model using the clinical data to predict the outcome. But that in and of itself isn't trivial. The data could often be very rich in the sense of lots of variables. So you need maybe only a small subset of those variables are actually relevant for prediction. And also sometimes you might need to think carefully about how you include those variables. Do you need to transform them or so forth? So the model building isn't trivial by any means. But then to throw extra sort of an extra spanner in the works is not only do you have like a lot of data to process and handle, you often have missing data as well, right? So when you're dealing with something like a clinical data set, which some of which may be observational, you're quite likely to have some of the data not being reported for various reasons. So these sort of red boxes here are sort of intending to sort of illustrate the fact that some variables are only partially observed. And of course, this is known in the literature, in particular statistical literature. And there's a lot of fundamental work on missing data. And if you're familiar, I won't go through all of this for time, but I think many people will be familiar with these sort of decompositions or taxonomies like missing completely at random and missing at random and so forth. But they tend to actually implicitly focus on more sort of univariate senses. So you might take one of these variables here and say, well, what's the underlying causes or processes that drive the missingness in this variable? So that there's a lot of great work and useful work done on that setting. But as we're perhaps all appreciating now, we're often dealing with things on a much bigger scale, lots more variables, and trying to handle much larger volumes of data. And missing data doesn't go away there either, but the challenges also increase as you deal with the size and setting of the data. Just to first briefly illustrate what's a relevant phenomenon here that hasn't really been explored much in the literature as you deal with multivariate data sets, is this idea of structured missingness. So the idea is you've got a big multivariate data set, lots of variables, and you've got missing data in those variables as well. The previous illustration sort of expanded on in the left panel here is sort of is essentially what we might sort of have typically viewed the problem as, which is essentially missing values spread out seemingly, randomly throughout, the space of the, incomplete sort of part of the data. And that might happen. And we call this unstructured missing data. But that isn't really the only way that missing values can occur. And there's a particular type of setting or problem, which is very, very relevant for what we're going to consider in integration in a minute. But that's where we have some structure to the missing data. Okay, so this is essentially where there may be some relationships, or of course, another word is structure, that sort of relates the missing values to one another. And you can kind of see this through this sort of spectrum. I guess I've called the left one very weak structured missingness, or almost like no, it could be no structured missingness, all the way to the right, which is the strongest structured missingness. So the most extreme, I guess, is you could have a block of missing data. So that essentially means if you're missing in one of these 4 variables, you'll be certain to be missing in the others as well. So there's a very strong dependency between missingness and not missing. but you can also have sort of things that lie sort of in between the two. So you may not be guaranteed to be missing on all four, but if you're missing in one of these four variables, you're more likely to be missing in the other three than you would be if you weren't missing on them, for example. So this is what we say, sort of talk about an almost block. So there's different amounts of structure that can occur, and there's sort of and there's different reasons and different sort of ways that can happen. So this is sort of the idea, the general idea. There's relationships between whether you're likely to be missing in one variable and other variables so that's the just general idea. But let's sort of see why this might be relevant now in sort of simple settings, gradually moving on to something more complex and practical. So this is perhaps one of the simplest illustrations I can think of about why we have some specific challenges to deal with structured missingness that aren't necessarily the case in other types of missing data problems. So this is like for example, a clinical type data set you could imagine. You've got various demographic and other types of attributes recorded. And one of the measurements you have is prostate specific antigen score, right? So I guess what I want you to think about, I guess I could have had a poll now question, but I guess this is about quite obvious, is that we've kind of split up, ignore the sort of multicolored box, but we've split up the, these missing observations, I guess, into two colors. And so the red ones are actually, are specific types of missing values, right? Because this is a PSA measurement, which is a prostate-specific antigen score. And that only makes sense to measure if your sex is male, right? So it's not a surprise that some of these missing values are there, or at least some of these values aren't recorded, let's say. And so if you were to throw a standard imputation package, mice is a very convenient one, and it wasn't, this wasn't sort of somehow coded into the routine, it wouldn't realize that, and it would just seek to impute something for these values. You could impute something, it just wouldn't make any sense, clinically. So this is a very simple example of structured missingness where there is, a reason why some variables are supposed to be missing. And of course, in a simple setting like this, you can maybe try and get around it. Or make sure that your model or your imputation is it respects that. But as you deal with many variables, this kind of thing becomes a lot more complicated and challenging. With the multivariate setting essentially comes into play. But even in this setting, you have to be a bit careful, because if you look at this this sort of multicolored sort of two boxes here, where someone is missing gender and PSA. And if you think about an iterative procedure that imputes variables one at a time and conditional on one variable, you impute another variable. Depending on how you imputed the missing gender would determine what you might want to do with the missing PSA score here. Because if this was imputed to be male, then you could plausibly impute this missing PSA value, whereas if it was imputed to be female, then you couldn't. So even in this relatively simple setting, you can start to see problems occurring, basically. So the idea is imputation is, I certainly have, I like imputation, and it has many benefits, and many people here will probably appreciate that. But the idea, I guess, from a simple setting is we know that there's some things we're not supposed to impute, and we need to handle that. And we also know that there are some missing values we can impute. And the structured sense of the problem determines in this setting what we can and can't do. This is just one instance of structure in missing data. And so how do we best utilize the imputable and non-imputable missing values as we build our ultimate model? Because remember, the goal is to build a predictive model sitting on top of this, right? So that's the sort of overall scheme of like how the structure is an important challenge to overcome. And you can start to see more complex settings, and Elrozy will be talking about some more practical illustrations of structured missingness that have to be overcome. But before we get into something quite contextual, I just want to talk a little bit about how data integration fits in here, because we really want to sort of utilize our understanding of structured missingness to facilitate some challenges in data integration. So before, we were talking about building a model for clinical data. Let's say it's on, say, 2,000 people with 100 variables, and we want to build a predictive model for some outcome Y. And now suppose that we have some extra set of data. So it's not just clinical, but some genomic measurements that have been taken on a subset of individuals within our 2000 sort of patient group. And we want to utilize both of these data sources. So we're just calling them C and G for short, to predict for the outcome Y. So that's a data integration challenge, right? Integrating two different sources of data in order to build a predictive model. But what we can do is, using our sort of idea of structured missingness, is we can invert this problem and view it as one of structured missingness, right? So if we sort of put the data sets together, so remember G is like a subset of C in terms of the individuals, then we've got a portion of the individuals that are measured on both C and G, but we've also got a substantial portion of, I guess, what we can view it as missing G data on the remaining individuals in the clinical data set C, right? So you're either measured completely on the G variables, or you're not measured at all on the G variables, and that's just comes back to that definition of block missingness. It's also important to note that we're not ignoring or trying to seek to deviate from well-known taxonomies or concepts in missing data. So we're not saying that you should think about this and not think about missing completely at random, missing at random, missing not at random. These are equally, if not more important in these settings due to the multivariate nature. But this is an additional layer that can perhaps exacerbate or have additional consequences that we have to address. So, you know, for example, missing completely at random has often been seen as the least interesting and simplest one to handle. And that may still be the case here, but there's still structure that can happen with missing completely at random. So, you know, for example, units missing G might just be a random sample from the units in C. Just some people were lucky and had their genetic measurements taken, some people didn't. Whereas maybe some of the units missing G are more or less likely to occur based on the C data. So, you know, if you think about, you know, this was something to do with genetic tests to determine risk of prostate cancer, then presumably the female group wouldn't have these genetic measurements taken because that's not really of, you know, clinical relevance there. And you can think of, you know, other more complex settings involving multiple clinical variables that drive whether or not people are missing or not in this G data. And you can even think of missing not at random examples too. So there's a lot of richness that this adds to the whole scope of missing data multivariately. Of course, missing data can also be part of, you know, these blocks of C and G as well in different ways, structured or unstructured. You know, think of the other sort of the almost sort of the weaker structured missingness, for example, that can still appear in other parts of the data. Okay, so just to sort of briefly talk about a simulation, this is very early days, and we still have a lot of thinking in development to do in this part, but it's just worth to show you all the kind of the direction we're going with this. So we sort of simulated some data following this scenario, saying that we have some clinical data, genomic data following T distributions, just to be a bit more funky than normal. And they had a 3 degrees of freedom variance one. These were chosen arbitrarily for now and can and will be explored, you know, through different settings. And we had correlations between the C and G variables of 0.4 and correlations between C and G with 0.2. And our outcome variable is just assumed to be normally distributed. And just in the spirit of model selection, we didn't make it dependent on all the variables because that wouldn't be that practical. So we assumed it's dependent on the first 10 clinical variables out of 100 and the first 70 genomic variables out of 100, with the effect sizes varying from the C to the G data. And we also put in some missing data in C, and we assumed it was sort of weakly structured using a copula, which I won't go into details now, but we've got sort of some theory that we've developed on how to, that our postdoc Jackson has developed on how to simulate weak structured missing data. And we just for simplicity, we didn't put any missing data in G, but we could have done, of course. Okay, and so what we're going to do is we're going to impute our unobserved block of missing data. And this is something which, of course, is perhaps skeptical because people are sort of, you know, understandably will see this is a huge kind of chunk of data that doesn't exist, and we're imputing it. But the idea is with a view of data integration, right? So the idea is you're imputing that data to allow predictions to be made using both C and G in an integrated way. So now you can sort of view this as a bridge that's integrated the C and G data together. And now you can use this combined integrated data set involving the imputed values to build a model for prediction model for Y. To build a predictive model, again, there's not many choices. Just we settled on a very popular one called Lasso that we won't go into, but it essentially helps to sort of filter out the less predictive variables in C and G and sort of upweight the more predictive variables. It's been shown to have good predictive performance. So it's a well-known model that's used for prediction and sort of when you have a high dimensional problem. And we're going to measure predictive performance for a classic train and test set. So we have a test set which will predict for and look at the mean absolute difference between predicted and actual Y in the test set. So that's our kind of integrated way of doing things. But we also want to think of other ways that don't use imputation and think of it in maybe a non-integrated way, at least for now, because, you know, there's many different approaches here. So we take a non-integrated approach where we actually split the data into the two groups. So one group has both C and G observed, and another group has just the C data observed. And we just make separate prediction models from the two groups, basically. And then, of course, we have missing data in C. So we still have a bit of imputation going on to impute the missing data in C, but they're fitted through the separate data, basically. Separate groups, sorry. And we measure predictive performance in the same way. So just to briefly briefly end, I guess, at my part. So we look at this in a simulation setting, and we look at sort of the mean absolute differences. So smaller numbers are better here. And so what we did is we broke it up, because this is another aspect of prediction. We often lump everyone together, whereas in fact, that looking at it on a more personalized setting is more appropriate for the practical sense, because, you know, there might be some people we're able to do better for than others. If we break up the data into these two groups, and we look at these sort of group 1 individuals where we're measured both on C and G, and group 2 where you just measured on C. And if we used the sort of integrated approach through imputation, so one model for the whole data, we can see that it does similar in the group 1 individuals compared to the approach that does, you know, look at that difference, breaks it up into two models. But it does a little bit worse in the approach where you actually split it up. So basically, your imputations aren't really helping your prediction model in the group 2 data, which is this model here. So you're sort of utilizing some imputed values here, but they're not really helping to in the way that we might like in this very sort of early simulation setting. So so at this point, there's evidence to suggest in this relatively clean and simple setting, building separate models may be slightly advantageous, but I think we're quite certain that other scenarios might lead to other profiles. And you can think of ways where you're integrating multiple data sources where it's less convenient to do this sort of separate approach of sort of breaking things up into different groups. So in particular, we think it'll be very specific to different settings, and our intention is to develop, you know, not to necessarily advocate for just one method only here, but to develop a range of methods which involve also non-imputation approaches to best integrate the multiple data sources to develop prediction models. So we're trying to lay a template going forward for, well, these are all the options we can do and what works best for a particular scenario. I will stop there. I think I may have overrun. I'm sorry, Vicky. I will hand it over to Elrozy now for her part.
No, I think you're all good.
Okay.
Cool. I think
I'll stop sharing it.
Yeah, share her screen.
I guess everybody can see my screen now.
Yeah, that looks good.
Yeah, thanks, Vicky, first of all, for the introduction, and Robin for the nice presentation, introduction to structure missingness. So I will now move forward to an application which comes from a real-world data set. So nowadays we are flooded with a lot of information in every aspect of our lives, and the same happens in health industry. Due to electronic medical records, we have now a lot of information that we take for our patients. So a nice comprehensive data set is the US Cystic Fibrosis Foundation patient registry data set. So cystic fibrosis is a genetic disease that mostly affects the lungs, but also the digestion system. So back in the 19th, patients were not living further than 30 years old. But now, due to the new treatments that we have, this has changed. So up to now, I would say, okay, these figures show up to 2019, but up to now, I know that people could live up to 60 or 70 years old. So that's good news. So a small sneak peek of the data set. So it consists of 35,000 patients, a little bit more actually. And these patients have more than 1.5 million observations. So it's a high dimensional data. The median baseline age is 9 and almost 50% are females. The median follow-up duration is 10. So in this data set, we have different types of information that are collected that we want to investigate also and are important for the disease. So we have some baseline characteristics, and for now we are using some important ones from the clinical point of view, such as sex, age, genotype, socioeconomic status, whether the patients have insurance, and whether they have some type of infection or not. Of course, we have some more complex data sets, such as biomarkers, so measurements that are taking over time. An important one here is FEV1, which measures how much oxygen a patient can inhale. And of course, this is important to monitor because, yeah, I mean, these patients get they can get infections in their lungs, and therefore it's important to measure the oxygen that they can inhale. And finally, these patients tend to be underweight, and therefore it is important for the physicians to monitor their BMI. So the first question that we can have here, the first research question is, how can we handle patients that dropped out due to death or lung transplantation? So as you can imagine, these patients are of high risk of dying because, yeah, they get all these infections, very common infections in their lungs, and at some point either the lungs can't handle it, so they're dying, or they will need a lung transplantation. So you can also see that those patients get really early lung transplantation if possible. So in this list of data set, we can add that we have survival data, so we have the time to death or the time to lung transplantation. And in these plots here, you can see for some randomly selected patients, the FEV1 measurements over time. For patients on the left side that didn't have the event, so they didn't die or had transplantation, and on the right side for the patients that had the event. So as you can see, patients that had the event have less measurements, obviously, and if you look closely, you can see that those measurements are lower, so they are dropping faster. So just to mention that for the FEV1, higher values mean that you're healthy, your oxygen levels are fine, but values close to, let's say, under 20, I don't know how low we can get, but I guess it can go negative or 0, then it means you're dead, means that, yeah, there is a problem. So in order to illustrate the problem here that we have, I created this figure. So what I'm presenting here, I have in the x-axis age, the y-axis FEV1. So the circles, the black circles, represent the observed data that I have from 20 randomly selected patients. The solid line here represents the evolution, the smooth evolution over time. So what I did here with the blue points, I simulated some extra FEV1 measurements for the patients that died and had a lung transplantation. And of course, I expected those values, the FEV values, to be lower than the previous one. So when I simulate some data and then I model the data again, I get my smooth curve, I can see that this evolution is different. So that gives me the feeling that by ignoring this information, yeah, you might get a wrong a representation of the evolution over time for the lung function. So the data set is obviously missing, not at random here. So the patient died because the lung function is really bad. So it dropped really low. So an approach to take that into account is to jointly model the outcome of interest with a missing data process. So in our case, the outcome of interest is FEV1, or someone could think of BMI. And then the missing data process is the time to death or transplantation. And there are some models that have been used in the past. So we have the selection model, pattern mixture models, or the SER parameter models. So with this application, we focused on the last one. So the SER parameter models, or one specific case of those, the joint models of longitudinal and survival data. And the idea is to model everything jointly. So if you look at this equation, YO denotes the outcome of the observed data, YM is the outcome for the missing data, and R is the missing data process. So what the idea is that you model those things together and you introduce some latent variables, here the BIs. So given those BIs, you assume that the outcome of interest and the missing data process are independent. So we apply this modeling in the data set. And now I will move to the second research question. So how did we use this modeling in order to further model the data? So one question that we got also from the patients that have cystic fibrosis is, where is the best place to live with cystic fibrosis? So to me, this was translated into prediction models. Patients would want to have some prediction models in order to see, okay, where is the best place to live for them. So if you want to translate this research question into a statistical model, what I thought of personalized dynamic prediction. So personalized because every patient is unique and you need to account for that. They will have their own, let's say, future measurements. Dynamic because, yeah, these measurements are updated every time and new information is available. So these patients are monitored and therefore new data is available. So we have the scenario where we have a new patient L, and then using all the baseline information that we have, for example, as we saw before, sex, gender, and so on, and using all the longitudinal outcomes that we have, for example, FEV1 or BMI, then we would like to obtain the future longitudinal outcomes or the probability of those patients surviving in a clinically relevant interval. So if we translate that into formulas, basically using the joint models introduced before, we can obtain the mean value of the future longitudinal outcome at a particular clinically relevant interval, given all the previous information that we have, so all the previous values of the biomarker, and we can also calculate the probability of surviving, so not experience the event in a clinically relevant interval, given that up to this time point, up to now, they didn't experience the event. And of course, before we go ahead and we present the prediction model to the doctors or even to the patients, it's good to evaluate that. So yeah, we can evaluate in different ways. So first of all, we can evaluate the longitudinal and the survival outcomes by calculating the distance between the predicted outcome and the actual outcome. And we can do that either with bootstrapping or a cross-validation procedure. And for the survival outcomes, we can further investigate how the longitudinal biomarker can discriminate between subjects that had a low and a high risk, so the so-called AUC. Just in our case, the AUC will be dynamic because remember that we have more information available for the patient every year. So going back to the applications, we have investigating the following. So we have the outcomes FEV1, BMI, weight, height, and exacerbation. So exacerbation is seen as a survival outcome as well because it's the event when the patient needs to be hospitalized and needs some intravenous treatment. And what we want to investigate here is to investigate whether including growth markers, so for example, the BMI, weight, or height, would further improve the predictive performance for the survival outcome. First of all, I will show you some predictions. As I said, these are dynamic prediction and personalized. So here we can see the measurement of a particular patient. As you can see in the y-axis, we have the FEV1 and the BMI. The x-axis, we have age. The circles represent the information that we have of the biomarkers for this particular patient. And on the right-hand side, you can see the event-free probability that is being updated as more information is available on the patient. And yeah, here we evaluated those predictions. So each panel shows a different model, assuming different outcomes. So in the first one, we have only FEV1. Then we investigate FEV1 with weight, FEV1 with height, FEV1 with BMI, and finally FEV1 with height and weight. And in each figure, we have different box plots, and each box plots focuses on a particular clinically interval window that we want to obtain those predictions. So for example, in the first box plot, we use information up to 12 years, and we predict half a year later. Next box plot, we assume information up to 12 years, and we predict the next year, and so on. So our conclusion here was that the predictions were not really improved by changing the outcomes. So I investigated the AUC, as you can see, and the higher values of AUC indicate better prediction models. So we didn't see a lot of differences there. Then, of course, we still wanted to improve those predictions in order to answer the question, okay, where can a patient with cystic fibrosis live? So we thought about integrating different types of information. So our list of data increases even further. There has been an interest now involving environmental and community factors in the analysis of cystic fibrosis patients. So we try to do that. And also there is a tendency to use image data. So there are a lot of CT scans that are taken in these patients in order to monitor the structural airway abnormalities that are in the lungs. And yeah, when I thought of this extra data, I could imagine the nice plot of Robin, where he has the C and the G data. And yeah, the question is, how do you combine those? Because of course, in that case, we have some patients that will not have all the information. So they will be missing FEV1, but they would have the geomarkers. They would have maybe image data, but they will not have FEV1. So we have this challenge. So even more, we tend we want to use more information, then we would actually end up with less patients. So that's why I'm wondering, yeah, in this case, more is less actually. So for the geomarker, we use the deprivation index. In the US, there are many socioeconomic variables that capture this community deprivation index. And because these are really highly correlated, you can include them all together in the model. So what some researchers did is to apply principal component analysis in order to combine them. And they use the first component, which captures 60% of the total variability, and they call that deprivation index. They rescaled it and normalized it in order to range from 0 to 1, where 1 means that that is highly deprivated. And what we next want to do is to associate that with FEV1. Here, first of all, you can see how this marker looks like. How does this geomarker look like? So I again selected random patients per state, because of course, the patient asked, where should I live? So I thought, okay, let's investigate that per state. So what we first notice is that this marker doesn't really change a lot over time. There are every now and then some steps, but it's mainly stable. So our thought was to investigate whether, how long you have been exposed would influence FEV1, so your lung function. And therefore, for each state, we investigate the area under the curve of the deprivation index to be associated with FEV1. And here you can see the results. So we have the estimate in each state and the standard error. So you see that in some areas, there is a high correlation between deprivation index and lung function. The gray areas means that the data set were not enough to apply our models. And of course, if you further look at our data set, we have this image. So we have a lot of extra values coming for some patients. So if you see at the lung, you can see how it's structured. So all these little veins and tubes get values. So we can also incorporate that in our analysis. So it would be great to see if we can use this in our already built prediction model, and whether this would further improve the prediction of the patient, and we can finally answer this question, okay, where should a patient live?
I think we're just handing over to Robin now, right, for conclusion.
Yeah, I think Elrozy kindly put the last slide on there. But no, thank you very much. It was really interesting, Elrozy, as well, to complement the sort of clean theoretical side of things with all the complexities of a genuine medical challenge, with all the statistical complexities as well there. And I really like the phrase you used which I think is actually very, very relevant in general as well, which is more is less sometimes, or at least in the sense that you have to be careful, particularly when you talk about predictions and for looking at personalized predictions. Just simply throwing extra data at the problem without careful consideration of how you utilize the extra data could have a detrimental effect, certainly on certain groups, even if it's at the expense of improving some other groups. But so there are lots of challenges in data integration, and structured missingness sort of is a key one. And we've hopefully, and from the poll, I hope that it seems as well that we've shown how this sort of is highly relevant in data integration. Obviously, some simple simulations have sort of started the ball rolling through how do we kind of investigate this. Imputation is often a go-to, but it isn't a panacea, and we've seen just an example of that here. If we're not careful, just simply throwing imputation at the problem isn't always ideal, or at least sometimes we know we can't do it as well if it's if there's reasons that the data's missing. So we want to explore this in a very open way, considering all different ways we can integrate the information from different data sets. Sometimes it may be imputation, sometimes not, and we're sort of, our sense is that a combination of different approaches is likely to be optimal, and it's going to be quite data or problem dependent. And just to again, to thank Elrozy, like her example involving the cystic fibrosis data is very, very nicely illustrates the scale of the challenges that we can encounter in practice, but also how it's really important. So if we can address the structured missingness, then the potential to greatly improve how we utilize complex integrated data sources, ultimately translating into better patient care, is very evident. So thank you very much, Elrozy, and thank you very much for attending. I guess there's a thank you slide Elrozy had, so but I'll just say it now. Thank you.
Thank you so much, both. As Robin said, I felt like it was really nice to have the kind of foundation and then the real world kind of situation. We've now got around 10 minutes for questions. So you can pop your questions in the Q&A box, which you should be able to find in the bottom Zoom bar, or you are welcome to raise your virtual Zoom hand as well. And you can ask your question if you just want to unmute. I can see a question in the bar. So Kimberly has said, I wondered whether you can recommend any more general resources, such as textbooks or review papers, when approaching data integration, so not specifically structural missingness. I'm a clinician without a stats background and won't be able to do things like simulation, but want to at least understand the issues and what I can do with packages and R. So yeah, either of you two want to take that one first?
Just to say, Jackie, I couldn't see I don't know if I'm looking at the wrong thing, but is it in the chat, the question?
It's in the Q&A box, which is separate to the chat.
Oh, but is it on Zoom? Sorry, is it?
Yeah.
Oh, Q&A. Oh, right. Okay.
Yeah,
Sorry,
yeah.
right,
I was also confused before
I see it now.
popping up.
Sorry, I just wanted to.
Yeah, so feel free to have another read through. I think, it's definitely interesting hearing from a clinician as well, because obviously this kind of issue, like you said, is becoming more prevalent.
I mean, this I'm not sure how helpful I'll be. Elrozy working a lot more with clinicians may be able to add to this, but I'll just say that the area of data integration is a very big hot topic. We've been seeing some special issues in stats journals to sort of try and advance the area. So that gives the sense that there's a lot of unanswered questions that we need to greatly address, particularly from the application side. In terms of sort of things like packages in R, I actually don't know off the top of my head of anything that is sort of directly relevant for sort of data integration beyond sort of treating it like an imputation problem and filling in the gaps that sort of are there when you sort of have merged them together. The closest thing that I am aware of is, but which isn't necessarily going to answer this problem, but may relate to some other questions around this, is record linkage. So the area of record linkage has been well explained, and there is this sort of record linkage package in R. I don't know it off the top of my head, but I'm happy to follow up separately with anyone that wants to chat. But that's where, if you sort of think that there's sort of either directly you're linking people up, so you think this person was in this clinical data and this person was in another sort of data source, and you want to sort of try and sort of link people up like directly, or which is often the case is probabilistically. So you're not entirely sure you have got direct links, but you have a degree of confidence that these two people are similar enough to sort of link them together, and you kind of factor that uncertainty into your overall kind of model building. So there's like deterministic and probabilistic record linkage. That's the area that has been explored quite a lot. Not exclusively in the medical domain, probably more in the sort of census survey sampling domain. So yeah, I think there is an urgent need to do more on that in terms of like dealing with some of these. But I think people are doing stuff with electronic health records and things, but whether or not they've actually got the R packages, that are well known and well developed yet, I'm not sure. I don't know, Elrozy, if you have anything to add.
No, I completely agree with you. I don't think there is also one methodology to do data integration. I think there are different ways. And first of all, as you said, yeah, you put everything together and some values are imputed, or you can put everything together and then the missing cases are gone. So you're deleting observation. So I think, yeah, there's no one methodology that you could deal with that. And that's why you should be careful also which packets you use and what you are doing, because it happened to me that, yeah, people want to just combine data set, they do it, and then they end up with 5 patients, and they have no idea why. So yeah, you need to be careful. And I think I've seen also different ways of data integration. So you can do it before any analysis. You can just try to integrate everybody. You can perform separate analysis and then integrate the results or the predictions. Yeah, so there are many different ways. So I don't think there is one packet or one textbook focusing on that. It really depends. And as Robin said, is data and yeah, problem specific.
Oh, thank you both. Ling Long, I can see you've got a hand up.
Oh, hello. Can you hear me? Can you hear me?
Yes.
Yeah, thanks for your so informative talk. So I'm also working on the Missingness, especially for healthcare data. And I do agree that you mentioned like there's some Missingness, they're naturally like sparseness. For example, for dynamic data and stat data, they do have those irregular sampling rate, and they will form some sparseness and align with those Missingness together, but it's very hard for us to identify. So I was also interested about this part, how what the things going on to identify this too. And for the application side, me and my supervisor recently, we're trying to write a survey paper to the deep learning master for those imputation task. And we do find lots of work. They're focusing on not only the imputation task itself, but align with this imputed value. We're trying to quantify the uncertainty, which happened during, whenever the awareness for the data itself, or maybe for the master itself, whenever it's deep learning master or just simply statistic murdering master. And apart from the uncertainty, another thing would be lots of bias, especially for class imbalance bias, because lots of HR data we have the negative group, the positive group, but both of them they may have quite different missing pattern, and if we do them together, maybe our imputed data set already been biased by the class imbalance, and all the downstream conclusion based on the unbiased data sets is maybe make no sense. So I do want to discuss about this part. Thank you.
Yeah, no, I was so many great points. So I think that it's I'm not sure if we can really adequately cover like all these things, but I mean, beyond just to say that we're at least I'm in complete agreement that there's a lot of challenges, especially on the multivariate data. I'm just trying to see if I remember all the points, but certainly the class imbalance point around where you have maybe a huge, like a binary two classes, and one class just dominates the other. And then we know that that's a challenge when you're trying to do classification because of the class imbalance, and people maybe undersample one class, although that is not ideal because you're sort of losing some data. But and that can just translate into imputation and model sort of building and development. So there could be like a kind of a propagation of, as you say, bias and so forth that makes things worse maybe even than not doing imputation. I mean, in terms of sort of handling these things, I think there's the imputation uncertainty as well is very important. That's something that in statistics, of course, we're very aware of and try to advocate for. I didn't go into all the details, of course, here, but one thing implicit in our framework was multiple imputation, which is sort of to repeat the imputation process to sort of factor in the uncertainty in our conclusions. And again, there is a sense that is also needs to be developed more, because a lot of these methods were developed 30, 40 years ago, when there was a different type of challenge where we were looking at often more inferential type things like a mean or some sort of some property of the data, as opposed to here's a prediction for a person's outcome, and we want to build some sort of good uncertainty around these sort of quantities. So the uses for the data are also influencing how we should handle the missing data as well. And so we're very much aware of that. I think I think they're all highly pertinent and relevant, and again, they're very specific to certain settings, but at the same time are very highly likely to occur. And I think, as you say, when you have different missing data patterns and so forth, that can also have an impact in how you should handle them in a very multivariate setting. So the challenges are very, are big and are there, and I think obviously we're trying to tackle them, in a stepwise fashion, or at least build things up to get to a situation that we think we're doing as good as we can at the moment on. But there's a lot of scope to develop more and better methods, really, to handle this highly multivariate setting. I mean, the one thing that we tend to see, of course, which is not ideal, is that there's a lot of great methodological development on the multivariate setting, but when it comes to the missing data, that kind of development is sometimes seen as maybe not in the same with the same amount of sort of thought in some settings. So so I guess the key is that the two are one and the same. So if you're going to, if you wanting to build the best possible model, and as you said, like to avoid biases and things, the missing data is an intrinsic part of that, and so that should be treated with the same sort of rigor, as other parts of a modeling analysis are. I don't know, Elrozy, if you wanted to add anything to
yeah, perfect points. Maybe something to add that was mentioned and it's important is, because you don't know what the bias that is generated. You don't know if it's big, if it's small. So therefore, that's why we do sensitivity analysis with different methods, so investigate different things, because you don't know what they're missing data for a reason, so you don't have this information, and therefore you can't really measure biases. You can do simulations, but still in your real data set, you have no idea. That's why, we do sensitivity analysis in order to be more sure about our results.
So thank you both so much for your fantastic talks.